Welcome, folks. Video on a special type of matrix called a non-singular matrix. So we'll start off as we usually do with a definition. We'll talk about what makes a matrix singular or not. We'll talk about how to find it, and then we'll relate that back to what we saw last time, this characteristic of a matrix called the null space. So here's a definition. In order to talk about a non-singular matrix, we first need to identify whether a matrix is square. A matrix is square if it has the same number of rows and columns. In this case, of course, that number of rows and columns might be called n. We'll say the matrix has size n. Of course, if a matrix is not square, we'll call it rectangular. So the characteristic of singular is a characteristic that only square matrices can have. So if a matrix is square, it may be singular. It is non-singular if the corresponding homogeneous linear system has only the trivial solution. Okay, so if you have a look at a homogeneous system of equations where the coefficient matrix is square and that system has only the trivial solution, we say that the matrix is non-singular. Otherwise, we say that the matrix is singular. Okay, so here's a take-home message. To address the question of singular, we'll have a look at the corresponding homogeneous linear system. Okay, we know that a homogeneous linear system always has a zero solution. If that's the only solution, our matrix is non-singular. If there are other solutions, our matrix is singular. So a couple of examples. Here's the first example, the matrix associated with archetype A. So we'll show that this matrix is singular. We saw before that the matrix reduces to the reduced row echelon form with R equals 2 pivots, n minus R equals 1 free variable. In this case, the homogeneous system of equations has infinitely many solutions, not just the zero solution, so we say that A is singular. On the other hand, the matrix corresponding to archetype B turns out to be non-singular. Again, to address the question of singular, we'll have a look at the homogeneous linear system. So in this case, we see that the homogeneous linear system has n equals 3 variables, R equals 3 pivots. Therefore, this system has 0 free variables. The only solution of the corresponding homogeneous system of equations is the 0 vector. So we see that B is non-singular. You may have noticed that the reduced row echelon form of a matrix takes on sort of a special form here in the case of a non-singular matrix. We'll exploit that in order to identify a non-singular matrix. So a definition, the identity matrix, I sub m, is a square matrix. It's size m, and it has the special characteristic that every element on the diagonal is 1, every other element is 0. I'll point out that the Kronecker delta notation is pretty useful here. Some of you may have seen this before. The Kronecker delta sub ij is the function that returns you 1 if I and j are the same, and 0 if I and j are different. Okay, so it's real quick then to represent the m by m identity matrix, a size m identity matrix by the Kronecker delta. Here's an example of the size 4 identity matrix, and again, we identify the diagonal with all of the elements where the row and the column index are the same. Okay, so often we say that the identity matrix has 1s on the diagonal and 0s elsewhere. If A is a square matrix and B is a reduced row echelon form of that matrix A, then A is non-singular if and only if B is the identity matrix. Okay, so again, here's another example of an if and only if theorem. We'll go ahead and prove this theorem. A quick reminder on proofs of if and only if theorems. To prove the statement P if and only if Q, we must show that truth of P implies truth of Q, and that truth of Q implies truth of P. So we'll start off with the second statement in this case, assuming truth of Q. The statement Q is that the reduced row echelon form of A is the identity matrix. We want to show that A is non-singular. Well, as it turns out, we know that the corresponding linear systems A, 0 and B, 0 have the same set of solutions since they're row equivalent. Now, of course, the homogeneous linear system of B, 0 has the solution x1 equals to x2 equals all the way up to x sub n equals 0, right? Because the matrix B is the identity matrix. So therefore, the only solution to the homogeneous linear system where A is a coefficient matrix is 0. Okay. If the only solution is the trivial solution, we say that A is non-singular. Conversely, if we want to show that A non-singular implies that B is the identity matrix, recall that A non-singular means that the only solution of the corresponding homogeneous linear system is the 0 solution. Of course, if the homogeneous linear system has only the 0 solution, the reduced row echelon form of that matrix B has 0 free variables, so m pivot columns. And that forces B to be the identity matrix. Okay, so the take-home message here is that if we want to check whether A is singular, just have a look at the reduced row echelon form. If that reduced row echelon form is the identity, then our matrix is not singular. So that's sort of the upshot of this theorem. To address singular, have a look at the reduced row echelon form. Here's an example again, back to archetype A. We saw that the reduced row echelon form of this matrix is not the identity matrix. Therefore, this matrix is singular. On the other hand, the reduced row echelon form of this matrix B associated with archetype B is the identity matrix. Therefore, this matrix is non-singular. So a quick tangent, have a look at the worksheet. We'll talk about this a little bit more in class. Okay, let's go ahead and transition and talk about the null space of a singular matrix. On one hand, we know that singular matrices have a non-trivial null space, right? So to see this again, we'll reduce this matrix to a reduced row echelon form, and it turns out that when you do that, the null space is this set of vectors. Okay, non-trivial null space, yes, singular. Okay, again, this matrix associated with archetype A, we saw it singular, and we saw it has a non-trivial null space. On the other hand, the matrix associated with archetype B, we saw is non-trivial, and we saw this matrix is non-singular, and we saw that it has a trivial null space. So again, this matrix has a trivial null space. We know it's non-singular. Okay, that turns out to always be true. And when we say always, of course, there's a theorem. So here's the theorem. A square matrix A is non-singular if and only if the null space of A is trivial. That is, the null space of A contains only the 0 vector. By definition, a matrix A is non-singular if and only if the homogeneous linear system has only the 0 solution. Now, of course, the null space of a matrix A is exactly the set of solutions to that homogeneous linear system. Therefore, we see that A is non-singular if and only if the null space of A is trivial. Now, as it turns out, a non-trivial null space has implications for a non-homogeneous system of linear equations too. So here's a theorem. Suppose that A is a square matrix. then A is non-singular if and only if the linear system A comma B has a unique solution for every choice of the constant vector B. So we'll go ahead and prove this theorem too. So we'll start off by assuming that the linear system A comma B has a unique solution for all choices of B. Then, in particular, the linear system A comma B has a solution in the case where B is the zero vector. Of course, if the homogeneous linear system has a unique solution, then the set of solutions to the linear system A comma B is exactly 0, so A is non-singular. Conversely, let us assume that A is non-singular. Here, we want to show that the corresponding linear system has a unique solution. Of course, if A is non-singular, then the matrix A augmented by B reduces to some other matrix where the non-augmented part is the identity matrix. In this case, where the augmented matrix reduces to a matrix with n equals r pivots, we see that x equals c is the unique solution. Okay, so this is pretty cool. Non-singular matrices have unique solutions no matter what the right-hand side is. Okay, so here is our first theorem. This is the non-singular matrix equivalency theorem number 1. The following are equivalent. Equivalent means truth of one implies the truth of all of the others. A non-singular is equivalent to, A reduces to the identity matrix, is equivalent to, the null space of A is only the zero vector, which is equivalent to, the linear system A comma B has a unique solution for every choice of the vector B. So I'll have you have a look at this on the worksheet. In order to prove equivalent statements, we show that one implies the other, and that sort of if and only if works in all directions. Okay, folks, more on these non-singular matrix equivalency theorems as we continue the term, so watch out for those. Have a great day. We'll talk to you soon. Bye-bye.